Okay, good morning, Thanks for making it along this morning. This is Net Zero Technology Centre. I'm Graham Rogerson. I'm the head of our Net Zero Technology team here at the centre. This is Tech20. It's our kind of social showcase for technologies, companies that we support. And this is our beauty this morning. We've been involved with supporting Verlume and Mocean for a long time, over the past 5 to 6 years. So it's just brilliant that they're here today and that you guys are in the building. I've got a couple of housekeeping pieces to run through. So first of all, on the fire side, fire escapes in the corner there. So that's all where we're heading. If that's blocked, we're back up the first flight of slayers on the right and straight out the door. The muster point's two buildings down at the back of the dentist. It's all signpost. Follow myself and Rona. No coffees, please, over the next 40 minutes. Makes too much noise while we're online. And that's the last bit. The session is being recorded, so I hope that's cool in the gang for everybody here. Okay, what we do is 20 minutes networking, which we've just had. I'm going to pass over to the lads for 20 minutes of presentation, then 20 minutes of Q&A. Brilliant. So before we get going, though, just a couple of things. Maybe, first of all, Richard, you want to stand up, just introduce yourself, and then I'll ask you to do the same.
Right. So, hi, everybody. I'm Richard Knox. I'm the CEO and founder of Verlume.
Hi, good morning, everybody. Thanks for coming. Ian Crossland, so I'm the Commercial Director for Mocean Energy. Thanks.
Brilliant. I think that's us. We're kind of ready to go. We'll put on the stop clock. You've got 20 minutes. And then once it turns 0, we all will disappear. Over to you guys.
Great, thanks, Graham. Great, good morning, welcome. As we said, hope everybody's got their coffee and some food, and we can get into the presentation. So this morning, decarbonisation of subsea operations with wave power and energy storage. So Richard and I are going to give you an overview of what the project's about, what the technology looks like, and whereabouts we're at today in terms of the project. On the left here, you can see the subsea halo system here. We have the Transmark AUV garage, and of course the wave energy converter in the background here. So this was taken when we did the deployment offshore earlier in the year. Just a quick shout out to all our partners, as you can see on the right hand side here. So there's a number of them, and without them partners, actually we wouldn't be where we are today for the project. So particularly with NZ2C, who've been pushing this technology with us along the way since the start. So today we're going to really just focus a little bit more about phase 3, but essentially RSP project, Renewables Subsea Power, has gone over sort of 3 phases. Phase 1 in the early days back in 2020, pioneered through the Oil and Gas Technology Centre as it was at that time. And then we brought on some partners, Chrysler, which of course now is Harbour Energy, Modus was supplying the AUV or the ROV system. And then Mocean ECOG, of course, with the rebranding now in Verlume, and Baker Hughes also a part of the project. So we did the desktop design and feed aspect of that. We moved into sort of the next 2 years, 2022, where we actually had a slight change in some of the partners. Harbour Energy, of course, was reformed. Transmark Subsea came in and replaced Modus. They couldn't actually sort of commit to the project in terms of delivering an AUV. Which was getting a lot of commercial traction at the time, and we couldn't actually give them an exact date of when we're looking to sort of deploy it. So unfortunately, they couldn't support the project. Very keen to join us still, but essentially we looked at bringing somebody else to fill that gap, which was Transmark Subsea, and done a fantastic job. And of course, Wave Energy Scotland also, who've been pioneering our technology from the start, also came in and supported the project, which is great. So bringing 2 industries together. Decarbonisation and just transition within the oil and gas, but also from Wave Energy Scotland's perspective, we're looking for clean renewable energy to support Scotland and UK in general. So at that point, we did our onshore testing. So we looked at procuring all the parts to do that. We did the manufacturing, and then we did the SIT testing, taking the whole complete system together prior to taking it offshore and deploying it, which we did in the sort of start of 2023 in February. We were a couple of months behind schedule on that due to a number of reasons, but it's quite hard to deploy, as we all know, in the winter period. Vessel availability and those sort of things meant that we were a little bit behind on that aspect. And then to the offshore demonstration. as you can see on the video playing on the right hand side there, and at the same time we brought in Serica Energy and PTTEP, which is the Thai National State Energy Company there. Richard, do you want to just give an overview of the project?
Yeah, sure. So what this is, we've talked about renewables for Subsea Power project, but the schematic, the idea of this is just to actually give you the kind of overall understanding what is RSP. So this is the original schematic that we used at the beginning of the project. So fundamentally, Renewables for Subsea Power project is a power and communication delivery system that we do using renewable energy. So at the top, we have Mocean's wave device, which generates the power, converting it from waves, and also provides a communication port. And that's often one of the things that's not always so obvious, but it's really important that we can provide both power and communications. So on that wave device, we've got a 4G link. It could be satellite or other communication systems, but on the one that's operating at the moment, it's a 4G connection, which we can pick up the mobile network in Orkney, where we're actually installed. And then there's also satellite backup available there as well in VHF and other communication systems. So the power is then exported down to the Halo system, which is just shown in the centre there. So we are charged. It's a lithium-ion battery system, so we are charged by the power generated from the WEC, and then we condition that power and then distribute it to payloads. So one of the key areas around the business case for this is that you can use our system for multiple things. So the two applications, and Ian just touched on it there. One is the AUV dock. So we're a charging station for underwater autonomous vehicles. And also with the support of Baker Hughes, we're simulating a carbon capture injection site. So we're powering a control system. And the intent is that we can show that we can provide stable power and comms reliably, just as if it was plugged into a socket on a wall. So that's the kind of fundamental outline of the system. So this is the first commercial system of its type. And essentially what it is, it's a microgrid. So it's completely detached from anything else. All the power and comms are completely separate, and we're doing it at commercial scale. So we're operating this just in the same way as you would in any kind of application commercially. And then the kind of key part of this area of the project, as Ian touched on, is not just showing that in theory it works in principle, but just the robustness and showing that we can work in all manner of different weathers and keep that stable power, etc. going. And through this, we're finalising the last steps, and those are familiar with the technology readiness level. So by testing it, we'll be finalising it at TRL 6 and 7, so we're just then ready for full commercial use. And then that allows us for using the system commercially on a wider basis. So I mentioned there are two applications, but really it's a power communication system, but what is it we're actually looking to do with it? So there's a number of different use cases. It's about what we use electricity for. It's quite as wide a answer as that, because obviously we're looking to focus on using this offshore. But what we've got here is some of the kind of primary examples in terms of where we've had customer engagement and people looking to use our system. So first one here is umbilical remediation. So if you have a subsea asset at the minute, traditionally it would be powered by a cable that's getting electricity from a host platform, or maybe even an onshore facility that's effectively burning fossil fuels to do that. We can come along with an alternative, which is the RSP system, that can take over the power supply, often in instances where the system is beyond the design life, there's been some sort of electrical degradation. The other two, long offsets and carbon capture and storage, you could almost potentially kind of group these as one. So this is about providing the power and communication system to the controls element of subsea Christmas trees and manifold centres. So our system, cost-wise, is completely independent as to the location from the host facility, whereas in a lot of the carbon capture storage sites, it could be 100 or 200 kilometres, so laying a cable and providing all those power and communication services to a remote well site is extremely expensive. We can do that at a fraction of the cost, and also so you've got the fact that you're using renewable energy, so there's the CO2 savings associated with that as well. The other is the vehicle residency, which we touched on. So either as a kind of temporary or a longer term means of providing a charging point for an AUV. So removing the need for the vessel, you've now got a charging point on the seabed that they can then charge up and download the data. Ocean and leak detection. So in certain instances, you want to know what's actually going in the seabed, maybe be leak detection because you're concerned that some of your infrastructure has a leak, or it could be actually just around looking for background data before you actually put in an installation. And again, to carbon capture and storage, where you want to know what the background level of various emissions that are occurring naturally before you start injecting anything into your wells. And then to the far my left, brownfield expansion. This is really where people may want to be expanding the capabilities of what they already have in a subsea field. So things like adding extra sensors and extra monitoring, but the existing power cable and comms aren't suitable for upgrading, then you can add extra functionality into your system there as well. And then last but not least is decommissioning. So this is kind of primarily focusing on monitoring your asset or a well where the whole facility may no longer be there. So before the well's fully plugged and abandoned, you can actually provide power and comms and make sure that the integrity of the well is safe. So multiple applications, but the technology is effectively the same. And also, as I mentioned earlier, it decarbonises this. So this one is an outline of the installation methodology, but it's just to show you all the kind of component parts of what builds the RSP system. And so in the graphic, I just showed it as the kind of main wave device in a halo system, but there's actually a little bit more to it than that. So within the wave device, we have to basically transmit the power and communications down the halo and the seabed and back up again. So the primary method for doing that is an umbilical. And then we have a swivel joint that's located before the WEC, because also we need to be able to allow the wave device to rotate around depending on the direction of the tide. So it allows us the WEC to fully move, but it doesn't interrupt the power communications in any way. So just do that slip ring. Then we have the main umbilical down to a breakaway joint. So if the worst comes to worst from a safety case perspective, it can physically disconnect. But a really important part of that is that the WEC can disconnect from the halo system. But right down in the bottom of the slide, you maybe see that it's got an acoustic modem and transponder. So not only can the WEC communicate through the cable to the halo system and charge through that, we also have an acoustic link. So even when the two aren't physically connected, we can provide a low bandwidth communications between the two systems. So we've used that during kind of installation, and also when we come to retrieve the system. But it also provides a backup communication system if the cable is forever to get damaged for whatever reason. So it's some inherent reliability built into the system. And then you see just at the bottom, as it was in the photographs, the AV dock, and then we have the Baker Hughes SEMS built into the main protection structure for Halo.
Yeah, wow. Just looking at this timer, it goes down really quick.
That's
the passion of talking about technology. So I'm just going to very quickly, in terms of RSP qualification, so it's taken a number of years, as you can appreciate. So back from concept in 2015, going through actually wave tank testing, which is a really important part of what we're doing to demonstrate the actually viability at scale with the technology we have, all the way through design and procurement in 2019, and then we took it to 2021, where we tested the machine for about 5 months at sea, and I have a slide on that which I can talk to. But again, sort of 6 years pretty much from conception all the way through to actually deploying within the project. So as I mentioned, 2021 we did the testing. This was done at EMIC's facility. We did 5 months of testing at sea, which was really good. Some of the key learnings that we actually had from this was the power production. So we can maintain something like 5 kilowatts of sustainable power, but we had peaks, depending on the wave size, of course, up to 30 kilowatts. Communication was really good for the system itself. 99% systems uptime. So that's really important, because as you can see at the top there, we have a mast. Of course, that is the gateway where we communicate with anything that's connected to below. Really important to demonstrate that. Survivability, by design, it has a shed loading mechanism, so where it dives through the waves, much like a surfer would do when it's going out from the water break out to the sea. So essentially, you can see the machine actually dives within the wave itself and underwater. So that's because you don't want the machine to come out of the wave itself, because it'll be quite a lot of a slamming load effect on top of the machine, much like you see on a ship, for example. And then reliability. So we had no sort of major failures at all. We actually did some operational maintenance, where we actually went out, recovered the WEC. We did some routine maintenance and reinstalled it again, and we did that in about a 4-day window. So that's something else that we could demonstrate, actually recovery and then redeployment. So that was really good. And then at that point in time, we got the take up to about TRL 6 or 7. So hopefully by the end of this project, we'll get to something similar that range. That's a complete system which we're trying to demonstrate. And on this slide here, you can see, so two of the key things we have to look at in terms of when we do a design is deployability and also potential of energy production. So on the right-hand side here, you can see a heat map. This is a heat map example for the North Sea, for the global heat map for a 20 kilowatt rated type machine. So we use this thing called capacity factor. So you can see on the top right there, something like 40%, which would be equivalent to something like 8 kilowatts. And then 20% would be somewhere in the region of about 4 kilowatts on a 20 kilowatt rated machine. So we look at wave sort of energy potential. The other thing we look at is survivability. So on the graph here, you can see, for example, there's a scatter diagram. And what we're looking to here is to look at this sort of a 100-year return period. So what we do is you take a contour line around this scatter diagram here, and then we demonstrate that to see the conditions that we see in terms of survivability of the machine. So what we're trying to understand is the machine. For example, if you have a hinge itself, articulating, we want to make sure that within those conditions, it's not going to hit the end stops. So through this design process, we understand, can the machine survive at those type of locations where we're deploying it at. And the other thing is that the machine itself, so when we talk about wave, a little bit like wind, that you have this cut in and cut off perspective. With wave, you have it's more like two-dimensional, we have to consider as well. So when we look at things like the wave height and the wave period, we have to consider that as well at the same time. So this is all part of the process when we do the design of the machine itself, make sure it survives within the environment it's being placed into. And the other thing is with those type of conditions where, for example, it's going to become quite wavy, quite horrendous in terms of the environment, actually it will passively disconnect itself to protect the machine as well. So it does have that capability, or passively. We don't have to physically do it, it does it itself.
Yeah, yeah, so just
4 minutes left.
Just to touch on the technology in relation to the energy storage system. So long and short of it is that this became an evolution of a storage management system that was originally using a tidal energy system. And as a business, we completely pivoted because we wanted to make sure that really our storage system could work with any kind of renewable energy device, and that's where the relationship with Mocean first started. So I've got more of the details in terms of how that works in the next slide. But essentially, our first commercial scale system was 100 kilowatt hours. So that's for scale, the same as a Tesla Model S. And then we've moved on to testing in 2022. And then combining the two to give us the full RSP system. So basically, our technology is built up of 2 key elements. One of them is the packaging of lithium-ion battery packs in a 1 atmosphere nitrogen-powered housing, which is essentially taking cell technology that's using EVs and packaging it in a way that means that it stays dry and we get the performance benefit of the stable temperature of the seabed. So one of the things that can affect design life is the fluctuations in temperatures and performance, but the seabed is actually a perfect environment for it as long as you keep it dry. So you get additional performance by the fact that we can keep it at a set temperature and also use the seawater as effectively a radiator to keep it cool. And then the other element is the Axon, which is our intelligent energy management system. So it's designed specifically to take renewable power, manage that power, set it at the correct voltage to charge battery packs, and decide which of the multiple battery packs is going to charge to extend the life of the system, and do all the power conversions so we can take AC or DC in and then convert that to AC or DC out depending on the particular application and set the power rating of it. So that's really the kind of brains of the system that we've developed. So that's the thing that effectively allows us to create a microgrid and communicate to all the different payloads. So, from a power perspective, one of the kind of challenges with renewable power is the fact that it can be intermittent. So this is an extrapolation of some real kind of live data where we've looked across the seasons and what the renewable power system could generate. And then this is what you actually get available. So you can either always have power available right the way through all the seasons. And then at this point during the summers where there's going to be, in this instance, less power available. But this is just a case of deciding, well, how big a safety margin you're going to have. So that becomes a commercial discussion. The more batteries you have, the closer to 100% you can have. The closer it gets down there. And that depends on the criticality of the application. But it means that you can basically eliminate one of the kind of biggest challenges in terms of using renewable energy for critical applications by coupling the two systems together, and then that's what we've been proving.
2 minutes. Wow.
Yeah. So there's now a 50-second video. Essentially, this video is the footage that came back from the EUV. So this was then kind of downloaded and uplinked through the communication system. So this is the Halo system just doing a circular inspection, and this is just showing the EUV. So this camera is pointing on the Halo, and then this is us inside the EUV. You can see it reversing back, and it does the same when it actually docks with the system. So it's some pretty impressive footage, and they've actually got 4K cameras on there. So they can provide all the data. So this was just to show the principles. So we've actually done, let's go to the next slide.
Yeah, we've done roughly about 50 mission runs, I think, with the AUV so far. So very, very quickly, some highlights here. One of the key things we, in terms of 3.34 megawatt hours of total power generated as of August, which is really key. The other key thing is we've actually experienced something like 5.32 meter in terms of significant wave height, which is really good. We expect to see probably something like 6 meters in that area we're at right now. And the other key thing is the solar. The solar's been a really good thing. Richard mentioned about that, so keeping that constant power available, and we see it's very cyclic in terms of the conditions of the wave. Some of the benefits we've seen right now with the solar is the fact that we only have 500 watts of solar. We have a huge amount of real estate that we can upscale that to maybe 3 kilowatts. So that will help with the intermittency, where those periods where the wave power can't be generated, you can be actually utilising the solar to help put power back into the subsea battery storage system. So testing, 12 seconds, wow, boom. And so we're going to continue testing up until February, March of this year, which is really great. The 3 key things we're going to focus on is reliability, survivability, and controllability. Again, proving and enhancing what we're learning right now, but in the winter period as well, which we really want to demonstrate. So then, key takeaways, boom, that's it, we're finished. You can see the key takeaways on here. Richard's covered them really, really well. I think the key thing is, what sort of projects, you guys are potentially looking at that we can support you with the project. We're also interested in maybe how potentially you guys would like to get involved in the project as well. There is still an opportunity to do that. So we certainly like to have those discussions if the opportunity arises. Just like to say thank you very much for listening to Richard.
Good effort. We're just over the 20 minutes, so fair play to you. So we thanks for that, and there's a heap of stuff in there, and we're just going to reset the clock and run through 20 minutes of Q&A for sure. Put your hand up. I can pass this on to you. I think we need to use it through the Q&A for yourselves. As the guys are saying, this is where we're working with them just now to help secure additional funding to push this trial out that's currently ongoing out into February or Q1 next year. It means that the device would then be in the water over a year, which will be a fantastic achievement, and a lot of data from it. So happy to open it straight onto the floor for questions if there's anybody.
Hi, thank you for the presentation. It was amazing. So you put that almost the end of the presentation graph where we could see the reliability of the power generated, and you were mentioning that putting more batteries. But it was just when you had a graph on 70%, it was probably the lowest point on the right graph. Anyway, yeah. So in terms of that one, exactly that one. So in terms of seeing 100% means satisfaction of the system. But have you thought in any possibility of using the excess of power to do like hydrogen production or any other use that could come up with that? Or?
Yeah, so that graph there is the state of charge, so that's how charged the batteries are. So you can always provide power until the state of charge gets to 0. But it is something in terms of longer term storage for bigger applications. it's not part of this project, and it's something that it's come up in other ones where you can increase the volume of batteries, but lithium-ion battery packs are reassuringly expensive. But at some point, you're better kind of going to other points in terms of electrolyzers. But that's when you kind of get like multi-megawatt scale when you're looking at plugging into an offshore wind. The scale that we are in terms of subsea assets, it's the kilowatt scale, the hundreds of kilowatts. You're adding quite a lot of complexity and cost without that volume of storage to balance it. Where the specific crossover point is, I'm not entirely sure yet, but you're talking maybe 20, 30 megawatt hours potentially just with battery packs before there's a benefit to moving over to storing with other mediums. And a lot of that's to do with the speed of response, because nothing responds as a battery pack when you're trying to stabilise it. It's more because that is a power management and a buffer. So it is something that would be a sort of an evolution of technology, but it's not really anything else to say. And I think it's not really anything else that it's not within this, but it's something we can see in the future when we can really start to scale things up.
Yeah, I mean, on this sheet you can see the intermittency here with the wave generation, but now having the solar on the top, actually if you aggregate it up, we can actually remove a lot of that, which means then ultimately, those drops that you see in terms of state of charge and the available power changes. In terms of the scale of what we have today, we could only budget the size of the batteries to have within the project capabilities, but as Richard said, we can scale that up. Of course, the battery system, it's connected, can provide power to a number of different things. The two examples we have is the AUV and the SEMSTAR 5 for the subsea controls module, but it could do other things as well. Yeah. The other thing about the battery storage is that you size it based on the power demand for the asset. When it's calling for that power, it needs to have that. Again, if you have excess, like you said, it can do other things as well, potentially, as long as the operator always has that minimum requirement of battery availability to be able to exercise different tasks in the asset it needs to, as and when they need to. So that's all part of the learnings that we've been having is, how do we make this much more elegant, more efficient? And we know that, for example, with the solar panels on board right now, by 10 o'clock, it's already filled the batteries up. So we know after that point in time, we can export more power down to the subsea battery storage system that we're not doing today. It wasn't part of the project, but that's one of the key learnings we've had. And then if you scale that up to something like 3 kilowatts on top of the surface we have with the size of the machine, that almost in certain parts of the world could almost be equivalent to the same with wave energy power generation. So there are some really key learnings we're finding out from the project itself.
I mean, there's been plenty of instances where we've had too much power, we've had to dump it.
We've had to dump it. Yeah, we've been constantly dumping power, and that's one of the things about trying to make it much more articulate. We only now switch the machine on and off to generate power when we see that potential waves coming in, and we can harvest that power and then put it to storage. And then when we can't harvest it, or there's no need to harvest it, then we don't operate the machine, which all comes back into controllability, maintenance, and all that aspect.
Okay, fantastic. May I ask one more thing? This is for Verlume. So you mentioned something as well in terms of the battery storage. You mentioned that you had a system that was optimizing a little bit the charging. Obviously, that's a must. But in terms of the heat produced by the battery, is there a strategy? Proper strategy in place to deal with that, or is it?
I mean, that's the sort of one of the kind of biggest design inputs in relation to putting it on the seabed versus having onshore storage. So we do a lot of work in terms of thermal modelling, in terms of transmitting the heat to the pipe wall. So basically transmit all the heat to the pipe wall, and then the surrounding water acts as a radiator. So if you have it's like a container with energy storage onshore and on the top side, we have a climate control system to try and stabilise that temperature. We don't need that because we're basically transferring it to the pipe wall. So then it means you don't have all the overhead and all the management and the maintenance associated with the climate control system. You're just basically using all the water that's around about you to immerse it. So that's been a really big part of the work in terms of developing the systems. Even actually, you get heat from charging cycles, you get heat from the batteries themselves. And we kind of have sensors all around, and we've been using that to kind of validate the system's been working really well from a temperature perspective, because we're constantly getting information back and validating against the theoretical models. It's not an obvious thing to do batteries, but it's actually a really place for them.
May open it up to anybody else. Awesome.
Hi, great presentation. I've watched the Verlume, the ECG and the Mocean story for a while, so it's nice to see it all actually come together. So I've got a two-part question. One's a scale-up question, one's a take-up question. So what I mean by that is, going back to what you said there, Richard, about the 100k system, to what extent can you push it? You know, up maybe double or actually more. So that's one question, because one of the things that we're looking at the moment is cutting in sort of renewable tech for like decom projects. We need about 200 to 400k on the seabed. So that was, I was going to ask about a question about how you scale it, either on a multiplex basis, like a Lego basis, or you can boost power. So that was the scale up question. The other question is about take up. You've got a very good end user case summary of 7 different markets. The problem with a technology that can do a variety of, or can solve a variety of different problems, is the customer just needs to know their one, right? So I think it's about, the question is about, in terms of take up, which markets you're going to go after first. And those may not necessarily be in the North Sea. So I just wanted to get your feedback on which of those 7 markets in your geographical ones would you go after first? Really, that's it.
That's the first question.
Yeah, so in terms of scalability, I mean, you can see the wee picture there with the pipes and the 100 kilowatt power system. So just as you say, it's a Lego block system. So the management system works in a way that you can just keep on adding it. So the there's a smaller system that we've got there. We're also working on which can kind of get up to 500 kilowatt hours. But the system that we're looking at to scale up to be much bigger is basically 0.5 megawatt hour building blocks. And then that's kind of where I made reference to 30 megawatt hours, because we're looking at what's been done onshore in terms of like grid stabilization and things. You need a minimum of 30 megawatt hours. So we think that's probably the kind of natural limit where you might start changing to longer storage mediums like hydrogen or compressed or whatever the answer might be. But you can kind of provide that buffer. We're still kind of working through the economics and making understand is that actually where the limit is. Because in theory, some of the stuff with the offshore wind, you go up to hundreds of megawatt hours, but it's extremely, it's a big kind of system, and it's actually the best way of doing it. But you do need that kind of speed response. So the sort of 30 megawatt hour sort of limit for subsea applications, these kind of things, we've looked at quite a few with Mocean that have sat around this 500 kilowatt hour, and we've got designs and ones around that size, of even up at just over a megawatt hour. And another question was about the markets. Yeah. So the biggest pull through and the kind of strongest interest we get is people who've got two ends of the spectrum. One is the power remediation, because they've got existing assets and there's been some sort of installation resistance degradation, so they want to keep it operational, but things are failing before they should, as a backup. And then the kind of carbon capture and storage, because they're new but they're so far away from existing place. You're talking hundreds of kilometres. It's a renewable solution that reduces CO2, but economically it becomes a fraction of the cost of transmit all that power. That's probably two ends of the spectrum. I mean, we get lots of inquiries in between the two companies, but they're the sort of the two kind of bookends of where we see the pull through. And most of the people that are involved from a customer base within the RSP project, it's the remediation and CCS is the kind of
Maybe just add to that, I mean, in terms of scalability, so what we're doing with this project today and the size of the machine, it's more than capable of sort of 4 to 8 well subsea tiebacks sort of size operations. We're already in the advanced stages, let's say, of building the next size machine. There's going to be some press releases coming out for that as well, but that's the kind of hundreds of kilowatts. So you're talking about that, operating range 80 to 200 kilowatts, and so, which is again sizable in terms of power we can provide. Just to complement what Rich is saying, I mean, every operator around the world has stranded assets. That's fact. And so trying to maybe re-establish those stranded assets is an easier, let's say, solution for us to do right now. But we've got to demonstrate that repeatability, reliability, controllability. That's the key things to demonstrate. And the other thing is Rich mentioned about the carbon capture and non-offsets. We're talking to customers, 100, 200 kilometers tiebacks, even new assets that we're planning, and existing ones, particularly in the southern hemisphere, where the temperature changes to something like 20 degrees, causes a lot of issues with IR potentially that we're trying to deal with. So that's that's a market we're trying to address as well. And the challenge with decommissioning is also an opportunity. The problem with that is cost. So it's about how do we balance that. And then the other aspect is the business development aspect of it. We can look at models like CapEx, where procuring equipment, but also rental equipment in terms of the short-term applications. So power as a service, effectively. So there's those aspects as well we can cover.
Good. I didn't mention it. There's a issues to say as well as in terms of the EUVs. We're getting quite a lot in that area. Quite a lot. And I think a lot of that's because the EUVs themselves are advancing and becoming much more capable. And then, if you have to use a vessel for launching them, it can absolutely defeat the purpose a wee bit. So the whole methodology of having the EUVs to be able to manage the dock, etc. But there's not been that way of easily retrofitting a docking station. So if you're going to down a new purchase, it's really easy to add that when you're putting something new out there and having it available. So
I think that's your question is like the plates are spinning everywhere.
The problem with the plates spinning everywhere is you have to focus somewhere.
So one of the focus that we're getting towards is in the umbilical remediation, and the best shout I heard was potentially going down like the pipeline repair club route, and I think we're getting a bit of traction on that, so that might actually be the next stage for us after this phase 3.
The thing about that is, it buys you time. If you can deploy a system that gets reinstated so it keeps the well on production, for example, then it buys you time to make what is that next decision. Does that become a permanent installation, or does it think, well, actually we're going to order an umbilical, and that can be 2 years. Because what it allows you is to buy time, which is really important.
Come on, anybody else? Any other questions? I got a couple just to fill. Go for it.
Hi, I want to ask you is how you keep the wet stable on and the second one is because it will be dynamic in motion, so the umbilicals they will have a lot of cutting. So how often you have to replace them?
So then we have. You can maybe use the picture of the wake, maybe to show. So to answer your first question, so it's a slack mooring system on the wake, so it's attached to the forward part of the wake itself. So there's no tension actually on the wake itself, because we have mid-water buoys and things like that taking some of the weight of the mooring system. Of course, as you go deeper, and there's no depth limitation, it's agnostic to that. But in fact, got a lot of weight hanging off there. So it's a slack moored system, which then also, as Richard mentioned here, we have a swivel section. So it allows it to rotate to the direction of the wave, so it's always facing the wave head on. So that by design is meant to do that. So obviously you don't want any tension on the wet, because it then stops it actually doing what it's designed to do. So that's the second question was?
Dynamic fatigue.
We have to do a lot of, so we're not experts in that domain. We actually use third parties to do that dynamic umbilical modelling itself. That's a really important part of it as well.
Just to add what Ian's saying, so I'm not a wet designer, but it's good listening to him because he gives me the kind of basic understanding of it. So the wet, when it's generating power, pivots against itself. Other wave systems actually pulling the moorings and the cables, and then that's what creates a lot of the stress and strain. So it's the fact it's the reaction between the two elements that you see there. So you're not always you're not putting the same stress and fatigue into the mooring system and the cables that you read in that. And some of the earlier wave systems where you're having to kind of not pull against it and hitting against end stops, etc.
We did a presentation a couple of weeks ago, actually, a much longer one, and we go into the design of the wake and the options in terms of wave energy devices, and can actually show you the example that Richard was mentioned about the different types and what is the optimum type. I mean, the system we have is a hinge raft machine, so it basically articulates around the generator, around the hinge, and that's what drives the generator to provide the power. But you have to have the flexibility with the wake to be able to move within the wave conditions. That's really important.
Yeah, good question. It's a key.
Yeah.
Yeah.
Thank you very much for the presentation. Building upon that question, have you looked at areas where wave conditions may change rapidly? I'm thinking possibly hurricane scenarios and all that. are you looking at how it would apply to it, and or is it a scenario that is too dangerous that or too challenging that for now should be
I mean,
avoided?
as I really briefly touched on about the design, we look at the 100-year period return wave, and we take that into account. You know, we designed it for that, under that environment. Of course, it's not optimum for the machine to be exposed to some of these hurricanes. I mean, in reality, you know, you probably would like to potentially disconnect, because if a hurricane comes through, particularly Gulf of Mexico, we're talking about an example, you probably remove the rake on to protect it, because whatever is in that path is going to take it out for sure. So, but we designed it for that 100-year period wave. And you know,
Is it worth touching on the fact that you know the units that you can switch off in the hinge?
yeah, I mean, you have a modular inside system in terms of the generator, and basically it's looking to actually, you know, in terms of optimizing the power under the wave conditions it's exposed to, it can go into a passive mode where it switches off, because the challenge with that is it's really imparting a lot of torque, and ultimately you'll probably break something in the machine. So it will go into a safe mode effectively during those conditions, where, you know, it's not optimum for generating power. The waves may be huge, but it's not necessarily the best type of conditions to produce power. So we do take that into consideration when we're designing the machine, absolutely. And some parts of the world are obviously a lot more aggressive than other parts of the world.
That's what I found quite interesting over this phase of the testing, is the sort of algorithm and the program on switching the hinge, and how much of it is actually working is being developed as it's gone through testing. So it's actually quite clever to make it a bit more safer when the bigger waves come through. Yeah, probably one of the key challenges of
it is.
wave
Some of the learnings
energy
we're having, you know, how do we optimize that? So it's like 12 modules within the system itself, and basically then you can switch them on, switch them off, and it can, you know, there is a certain element of artificial learning in there as it's working, try to maximize the wave potential under conditions, and then try to forecast that, because we know, for example, 1 or 2 days or 4 days, let's say, we know these waves are coming through, and they're very predictable. And that's the key thing about wave energy. It's super predictable, so that we can harvest that energy when the best time is to harvest it, and then switch it off when it's not great to actually produce it.
We've got time for one more question.
Sorry. Can I?
Of course you can. Quick one.
Yeah, I'm just thinking about the take-up to different geographical areas. Have you thought about an intermediary column, the osmosis column power, where you connect the storage at the bottom to the wave at the top? So depending upon your wave, tidal, current conditions, you get two sources of power. That's just a thought. Like similar to the Statcraft osmosis power column.
Just an idea. Yeah, I mean, in theory, we could add multiple power sources, but we haven't.
You've got the solar one, I guess. So it's
I guess we've got two already. The theory is you can put a number of inputs in, and it will kind of manage them all. And same, I mean, we're showing 2 outputs, but our system's got 7 outputs, so it's designed to be flexible. Just checking it before we can bite size.
It's about removing that intermittency, so we can have different types of energy sources.
Yeah, so
coming in.
there's another TechX cohort from last year that got wave energy converters on the seabed they're testing at the moment. So my question was, you know, to give you more sort of reliability, you've got more than one power input, that's all.
Yeah.
on that note, we'll call it a wrap. Guys, thanks very much.